Hello class, in this video we're going to be naming and writing ionic formulae. So before we go into that, we're going to quickly review over what we covered in the last lesson, which was representing electron transfers. But in this particular example over here, I actually want to go through how do we actually represent the electron transfer process using the electron dot diagram. Last time we actually did one using the Bohr diagram, but this time we're going to be doing it through the electron dot diagram, which is going to be a lot more simpler since you don't need to draw all those other unnecessary electrons. So firstly, for lithium, we know that lithium is in group 1, so it's got one valence electron, so I only need to show that electron only, and chlorine is in group 7, so therefore it has 7 valence electrons. We know that in an ionic compound, they transfer electrons. So in this case over here, from the donator, which is always going to be the metal, so lithium donates its electrons over to chlorine, and chlorine requires one extra electron in order for it to have a complete outer shell. In doing so, this is how we actually represent the electron transfer process using an arrow. Therefore, lithium will now have a positive charge, a net positive charge, since it has more protons than electrons, and chlorine has a net negative charge of -1 because it gained an extra electron. For the second example, beryllium and fluorine, beryllium has 2 valence electrons because it belongs in group 2. Fluorine, on the other hand, is again in group number 7, so it has 7 valence electrons. In this example over here, beryllium has 2 electrons in order for it to become stable, so it will donate 1 electron over to fluorine. However, after fluorine has gained this particular electron, fluorine is now happy, he is now very stable, so he doesn't actually require any extra electrons. Since beryllium still needs to give off 1 extra electron, we need to introduce another fluorine atom which can accept the electron away from beryllium. So therefore you need to draw in an extra beryllium, an extra fluorine atom, and then draw another arrow to show the electron transfer process. Therefore, this is how you should actually illustrate your answer. Beryllium will therefore have a net charge of +2 because it has lost 2 electrons. Fluorine, on the other hand, will have a net charge of -1. For the third example, potassium sulfur. Potassium is also in group 1, so it has a 1 valence electron. Sulfur, on the other hand, is in group number 6, so therefore it's got 6 valence electrons. Now, we know that sulfur requires 2 electrons, so potassium can actually give away 1 of its valence electrons. However, sulfur still requires that extra electron, so therefore we need to introduce another potassium atom. So therefore, it could give away another valence electron. Now sulfur is happy, so now sulfur has an extra 2 electrons, therefore it has a net charge of -2. Potassium, on the other hand, will have a net charge of +1. And for the very last example on this slide over here, magnesium and oxygen. Magnesium belongs in group 2, so it's got 2 valence electrons. Oxygen, on the other hand, belongs in group 6, so it's got 6 valence electrons. In this case over here, magnesium needs to lose 2 electrons in order to have a full outer shell, and oxygen requires 2 electrons. So this is perfect. So magnesium can donate this electron over here, and this electron on this coordination site. Now magnesium and oxygen are both happy and stable. So magnesium has a net charge of +2, oxygen has a net charge of -2. Again, just to summarize, we can draw or represent the electron transfer process either through the Bohr model, which is a lot more time consuming because you need to draw all the extra electrons and electron shells, but we could also do this using the electron dot diagram, aka the Lewis dot diagram, which is a lot more simplified. So in the exam, generally both versions are acceptable. You can use either one, but it's good to have an understanding of how we do it using both cases though. The learning intention of this video is we're going to be predicting the charges of monatomic ions. We're also going to be naming ionic compounds, and we're going to be writing the chemical formula of ionic compounds as well. So what I have over here is I've got a Venn diagram showing all the different types of ions that you may encounter. These are the common ions that you generally see and that we generally handle with in the laboratory. The reason why I've actually separated these two is because on the left hand side of here, notice that you've actually got individual atoms, okay? So you only have one single atom for those particular ions, whereas on the right hand side of the Venn diagram, you can actually see that these ions over here, these charged particles, they contain two or more other atoms inside of it. So we refer to the ions on the left hand side as monoatomic because mono means one, just a single atom. Whereas on the right hand side, we refer to this as polyatomic ions. Poly generally meaning more, like a polygon, many sides to a shape. So that's where it gets its name from. So what we're going to be doing now is we're going to be predicting the charges of monoatomic ions. The way that we do this is we need to actually have this essential background knowledge before we could actually proceed. We already know that metals have a tendency to lose electrons, and because they want to lose electrons, they will often have a positive charge when they form an ion. So as a result of that, these metallic cations will have either a +1, +2, or +3 charge depending on the number of valence electrons it has. In contrast, non-metals have a tendency to gain electrons since it already has almost has a complete outer shell. So therefore, it will want to gain electrons and thus will have a negative charge. So these non-metals will either have a -1, -2, or a -3 charge. So the way that we actually predict the charge of these cations and ions is, firstly, we're going to need to refer to the periodic table. On the right hand side of here, notice that the periodic table that I have is a lot more simple because I've actually got rid of the transition metals. So all the elements in the middle section of the periodic table, I've eliminated that out just to make things a lot more simpler. The second step is we need to determine the number of valence electrons the atom has, and that is easily obtained by its group number. So remember, the group number is the column number. And then afterwards, step 3 is find out how many electrons it needs to lose or gain to have a full valence electrons. So let's look at the first example over here where we're going to predict the ionic charge of nitrogen. So nitrogen is over here. Okay, it is in group number 5, okay? And we often said that in order for it to have a complete outer shell, it needs to have 8 electrons. So in this case of here, since it has 5 valence electrons, it's more likely for nitrogen to gain an extra 3 electrons than lose 5 electrons in order to have a complete outer shell. So therefore, nitrogen is going to gain 3. By gaining 3, it's going to have a net charge of 3 negative because it's going to gain 3 electrons. Because you're gaining electrons, you're going to have a net charge of have a negative charge. Fluorine, on the other hand, is over here. So fluorine in this case belongs in group 7. It needs to have 8 electrons in the valence shell, so therefore it only requires 1 extra electron. So fluorine is going to gain an extra electron, and by gaining 1 extra electron, it will have a net charge of -1. We don't need to show the 1 in this case because 1's often implied. And the final example is calcium. So calcium belongs over here. It belongs in group 2. So since it belongs in group 2, metals often have a tendency to lose electrons. And since it's losing electrons, it's going to have a net charge of 2+ because it has 2 electrons in its outer shell. Therefore, it will lose these 2 electrons in order to become stable. Therefore, it has more protons, electrons, therefore positive charge. Alright, so what I'd like you to do right now is I'd like you to please pause the video right now so you can answer these questions and then compare your answers with my answers. So these are the solutions that you should be getting for phosphorus. So phosphorus is over here. So therefore, being in group number 5, it will therefore want to gain 3 electrons, so therefore it's going to be P3-. Remember, always write the number first followed by the charge. Neon, on the other hand, is a noble gas. So remember, noble gases are already stable. They don't actually form ions. They don't lose or gain electrons at all since it has a complete outer shell. It follows the octet rule. So therefore, I'm just going to be writing Ne because it's a neutral atom. It doesn't form an ion at all. Calcium, on the other hand, we kind of did this before. This will have a net charge of +2. Beryllium is also in group number 2, so this is also going to be Be2+. Iodine is in group 7, so it's going to gain 1 electron, so -1. Helium is a noble gas, so helium doesn't actually form an ion, so it will just be He. Sodium will be +1. Magnesium will therefore be +2, bromide -1, and so forth, so forth. So I'm just going to be showing you all these answers over here. You should obtain the exact same answers that I'm getting as well. All right, moving on. What we're going to be doing now is, since we've actually predicted the ion charges of monatomic ions, we're now going to be learning how we actually name these monatomic ions. So what I have on the left hand side over here is I've got over on this side of here all the common cations that you see, and on the right hand side you can see all the anions as well. Now, my question to you is, what do you notice about the names of the metallic cations? So if you look over here and their corresponding name, do you guys actually notice that for each of these ions over here, the naming of these ions don't really change at all? However, when you compare with the anions, so for instance, if you compare it with we know that fluorine is usually an F. When fluorine becomes an ion, so it becomes F minus, notice that it's no longer fluorine. We refer to this particular ion as a fluoride. So this is generally the case for all anions. So therefore, all non-metals that form ions in this case, we always generally change the suffix, meaning the end of the name, to an "ide." So just to quickly summarize, when we're naming metal cations, their name does not change at all. So looking at these examples over here, when sodium becomes an ion, so therefore when it loses its electron, it still becomes sodium, but we just add an extra word, ion, just to indicate that, just to differentiate between a neutral sodium atom versus a sodium ion. Another example is magnesium. So magnesium has 2 valence electrons. It will lose these 2 valence electrons and therefore it will become a magnesium ion. Notice again, the name is not changed. You just add the word ion after it to indicate that this is an ion, not a neutral atom. In contrast, when we're naming non-metal anions, so things are charged particles with a negative charge, the suffix, meaning the end of the actual name, it will change to the word "ide." So this is one example over here that we covered before. So fluorine, in this case, remember fluorine has 7 valence electrons. It wants to have a complete outer shell, so it will gain 1 electron. But gaining 1 electron, it now has a net charge of -1, so F minus. And the name of this particular ion now becomes fluoride. So we changed the "ene" part to an "ide." That's how we actually name these particular anions. Another example is sulfur. So sulfur has a different suffix over here, but again, we're going to be changing it to the "ide" suffix. So sulfur now becomes sulfide in this case over here. Alright, I want you to please copy this particular table into your exercise book and complete the table. This should be fairly easy for you guys over here. So please pause the video right now and answer them. I'll have the solutions present right now for you guys to compare. All right, moving on. So we're now going to be looking at some polyatomic ions, and I kind of introduced what polyatomic ions are already. We said that polyatomic ions are charged ions that consist, meaning it contains more than 2 atoms. So for instance, you've got a lot of polyatomic ions to work with over here. Well, you don't need to know all of these polyatomic ions. I will quickly show you very soon the common polyatomic ions that you will encounter. And notice that for each of these ones over here, you don't there isn't necessarily a way for you to name this. You just have to memorize this and learn the names of these polyatomic ions off by heart. So the ones that I really only need you to know of are these ones over here. So ammonium is a common one. Hydroxide, nitrate, sulfate, carbonate, and phosphate. So these are the formulas over here. So these are the only things that you really need to know. So please copy down this particular table. Please copy down this as well as this. You can copy down the other columns as well, but it's not really necessary at all. Lastly, this is the second part, I think, of today's lesson, is we're going to be naming ionic compounds. So when we're naming ionic compounds, there are 3 main steps that you need to follow. First step is you write the name of the metal ion. Remember, when we're naming the metal ion or the monatomic ion, the naming of the metal doesn't really change at all. So in this case here for calcium, for this particular ionic compound, you've got the Ca, which is the calcium in this case. So calcium does not change. It will become calcium. But this over here, this element over here is bromine. When we said that all non-metals, when it forms an ion, we change the suffix of it, so the end part of the name, into the word "ide." So if you do this, it will therefore become calcium bromide. Notice that I don't really care about the numbers, the little subscripts. So the subscripts are the lowercase numbers in this case over here. You don't need to have any words to address these particular numbers at all. Looking at the second example over here, this is the ionic compound over here. The metal component in this case is lithium. So remember, we don't change the name of the metal part. It's going to be lithium something. And the O over here, it represents oxygen. Oxygen is a non-metal, so therefore we need to change the suffix ending of oxygen to "ide." So therefore it becomes oxide. Therefore the name of this ionic compound becomes lithium oxide. This one over here is aluminium. Again, you've got an oxygen, so therefore it becomes oxide. Therefore the name of this ionic compound becomes aluminium oxide. So as you can see over here, the way we actually name ionic compounds becomes really, really easy if you know the rules to the game. Alright, so now we're going to be looking at more challenging examples where we're going to be looking at ionic compounds that contain polyatomic ions. So all you really need to know is that when polyatomic ions are used, use the name of the polyatomic ions in the compound. So you should have already copied down this particular table inside your exercise book, and you need to refer to these for now in order to answer the questions. If you do this over and over again, you don't need to refer to this table at all. It just becomes you'll be able to memorize it. So for the first one over here, NH4 in this case, that's ammonium. So as you can see over here, that is ammonium. So, and this over here is fluorine. Fluorine, remember, you need to change the suffix of it, so it becomes fluoride. So when you're naming the first one, it's going to become ammonium fluoride. Second example is you got a calcium, and over here SO4, that is sulfate. So when we're naming this, it's going to become calcium sulfate. You might wonder, why is my spelling of sulfate different from this one over here? Remember, in Australia, we often use PH to spell sulfur sulfate, whereas in the US, they use the letter F instead. Both cases are fine, but try to use PH instead. The next example over here, you've got magnesium. We don't change the name of that because the metals always stay the same. However, you've got over here NO3. So NO3 is nitrate. So the name of this is going to become magnesium nitrate. And for the final example over here, you've got sodium, and OH over here represents hydroxide. So the name of this particular ionic compound is going to become sodium hydroxide. Alright, again, copy down this particular, all these questions over here. There's no table at all. I've just Control-C and Control-V, as you can see. But please pause the video right now so you can answer the following questions. And these are the solutions that you should obtain for them. So first one is calcium chloride. The second one over here is going to therefore be potassium sulfide. The third one over here, I don't actually have this particular polyatomic ion that you had to copy, so you don't have to worry about this. But the name of this is going to be potassium permanganate. BaO is going to be barium oxide. This is going to be ammonium chloride. The next one is cesium chloride. The next one is magnesium sulfate. The next one is sodium bromide. And the last one is aluminium phosphide. So hopefully all of you answered the following questions correctly. And moving towards the last component of today's lesson, where we're going to be learning how to write the chemical formulae of ionic compounds. So firstly, what is a chemical formula? Well, a chemical formula is a way that we represent any chemical substance using pretty much the symbols of the element that's present in it. So the great thing about chemical formulas is that it indicates for us what elements or what type of atoms are present in the compound, but also the chemical formula also shows you the number of atoms that the compound has using subscripts. And we said that subscripts are pretty much the lowercase numbers over here. So in this case over here, for calcium chloride, it tells you that calcium chloride has one calcium atom with 2 chlorine atoms attached to it or bonded to it in this case over here. So in this case, please remember, subscripts indicate the number of atoms present in the ionic compound. The reason why we use chemical formulae is because it kind of condenses this lengthy word over here in just a few letters or so, with a few letters and a few numbers. That's the reason why we use chemical formulae as opposed to writing the names every single time, because it's just going to become too lengthy. All right, when you're writing down the chemical formula of ionic compounds, there's one important fact that you really need to know. So, and that is the net charge of an ionic compound will always be equal to 0. So what that means is that an ionic compound is therefore neutral in this case. It doesn't carry any charge at all. It's not positive, it's not negative, although it does contain those individual ions. Those charges of there, they cancel out and they become 0. Before I go through this example, I do want to say that you might say the word ionic formula, and that just is a bit more specific. That just means what is the chemical formula of this particular ionic compound. So please note this down inside your exercise book as well. We're going to look through this example over here to explain what I mean by this particular statement over here. So for instance, potassium nitride, this is the ionic formula for this particular compound over here. So in this case over here, this subscript over here indicates there are 3 potassium ions, not 3 nitrogens, just 3 potassium ions. So you've got 3 potassiums and you've got 1 nitrogen ion over here. We know that potassium has a positive 1 net charge because it has 1 valence electron, therefore it will lose this particular electron over to nitrogen. Nitrogen generally has 5 valence electrons, it needs extra 3, so it gains 1 electron from each of these potassium ions over here. Notice in this case over here, you've got pretty much a net charge of 3 positives with 3 negatives. 3 plus negative 3, so in this case remember positive and negative pretty much makes a negative. 3 take away 3 in this case equals to 0. So therefore, this is what I mean by the net charge of an ionic compound will always equal to 0. And this is always going to be the case. If it doesn't actually equal to 0 at all, that means your proposed chemical formula for that ionic compound is therefore going to be incorrect. So this is a very useful way for you to check whether your formula is correct or not. Alright, so there are 2 ways for you to actually arrive to the chemical formula of an ionic compound. The first one is pretty much the lengthening method, and this is when we were drawing the electron transfer processes using either the electron dot diagram or the Bohr model. But there's also a shortcut method, and this is the method that you should be using, but I'm going to be showing you 2 methods over here just so you have a better understanding. So first method is when we're drawing the Lewis dot diagram. So using the exact same examples as the pretty much the introduction to this video over here. When we're drawing the electron transfer process, this tells you how many atoms there are in that particular ionic compound. So for instance, for lithium chlorine or lithium and chlorine, when they form a compound, which is therefore going to become lithium chloride, we can see that there's only 1 lithium atom, 1 chlorine atom. So therefore, that the formula of this ionic compound is going to be LiCl. In this case, if you remember, we don't need these charges over here. They cancel each other out, so we don't need to include the charges at all. For part B in this case here, beryllium and fluorine, we can see that there are 2 fluorine atoms, there are 1 beryllium atom, so therefore it's going to be BeF subscript 2. Remember, we use a subscript 2 because the subscript indicates how many atoms there are in the ionic compound. Potassium sulfur, so when this becomes an ionic compound, we can see that there are 2 potassium atoms and there's 1 sulfur atom. So therefore this should become K subscript 2 capital S. So this is now potassium sulfide. And magnesium and oxygen, this becomes magnesium oxide, and there's only 1 atom of each, so therefore there's going to be MgO in this case. Again, using the Bohr diagram, so how do we arrive to the ionic formula? So for lithium and oxygen, we can clearly say that there are 2 lithium atoms and 1 oxygen, so therefore this becomes Li2O. And calcium sulfur, there's only 1 atom of each, therefore this becomes CaS. Alright, we're now going to be looking at how do we use the shortcut method, aka the CRISS-CROSS method, to determine the actual ionic formula of an ionic compound. So we're going to be looking at one specific example over here. So we're going to be looking at aluminium sulfate. Now I've got the 3 steps over here in order for you to follow. So the first step is you need to firstly predict the charge of the cation. So in this case, it just means predict the charge of the metal when it becomes an ion. So in this case, we know that aluminium is going to have a positive 3, whereas sulfate, you just need to refer back to the table from before. Sulfate is SO4 with a net charge of -2. Now, we've done step 1, we've done step 2 already. The step 3 says we need to exchange the ionic charges in a X fashion. So pretty much in a crisscross fashion. So if you're doing the crisscross fashion over here, these are the ionic charges, okay? We need to exchange them in an X-like fashion. So if we do that like this, our formula becomes Al subscript 2 bracket. The reason why we need to have bracket, because these bracket indicates there are 3 groups of the sulfate ion in this case over here. So this is how we actually write down the ionic formula of aluminium sulfate. When you have a polyatomic ion such as sulfate over here, we do need to include brackets if there are more than one sulfate ion in this case over here. Now, the common mistake that students often make is they might often crisscross the little 4 here, but remember, we don't crisscross the subscripts. We only crisscross the charges in this case, or the superscripts. So we're going to be looking at a few more examples over here so that you have a better understanding. So the first one is sodium sulfate. So first and second step is you need to write the ionic charges of each individual atom. So sodium is Na+, sulfate is SO4 2-. We need then crisscross them. So if you were crisscrossing them, so you crisscross the +1 with the -2, it now becomes Na2SO4. We don't need to include the charges at all, just the numbers. So as you can see over here, the numbers have actually changed. We don't need to again write the 1 over here because 1 is kind of implied, so you don't need to do that at all. The next example is lithium sulfide. So lithium is Li+, sulfide is S2-. We crisscross again. And if we follow the crisscross, it's therefore going to become, there's 2 lithium atoms with 1 sulfur atom. So it will be Li2S. Strontium fluoride. Strontium has a +2 charge. Fluorine has a -1 charge. Again, follow the crisscross. So therefore, it's going to become SrF2. Magnesium hydroxide is therefore going to become Mg2+ with OH-. Follow the crisscross. So if you do the crisscross for this particular example over here, notice this would indicate that the 2 will go next to the hydroxide, but because this is a polyatomic ion, you need to include the bracket. So therefore it becomes Mg bracket OH close bracket with a subscript 2. Next example is aluminium and nitrate. So again, if you do the crisscross method over here, this 3 goes next to the nitrate over here. But because nitrate is a polyatomic ion, you need to include brackets over here. So therefore the answer becomes AlNO3 with a lowercase 3 when you include those brackets. Beryllium carbonate becomes Be2+ with CO3 2-. So in this particular example here, something interesting happens. Now the 2- goes down over here, 2+ also goes down over here, but notice that in this particular example over here, those are the exact same numbers. What we could do is we could actually simplify this. Since there's 2 berylliums and 2 carbonates, if you do this, this could be simplified to 1 beryllium and 1 carbonate. So it becomes BeCO3. You always simplify if the number is pretty much divisible or exactly the same. Potassium oxide, so that's K+ and O2-. Oops, sorry about that. Again, follow the crisscross method over here. So therefore, this now becomes K2O. Rubidium and nitrite. So rubidium is Rb+, nitrite is N3-. Again, follow the crisscross. This becomes Rb3N. We're now going to be looking at how do we find the ionic charges of transition metals, and the short answer of that is we don't really know how to, I guess, predict what its ionic charge is going to be, because all the transition metals, they kind of behave very differently. That's why it's a bit hard to do so. However, all questions will tell you what the charge is because they often use Roman numerals to indicate what's the charge. So for instance, silver, in this case, if you notice that I'm not using Roman numerals at all for silver, although silver is considered to be a transition metal. Silver is right over here. Silver always has a net charge of +1. That's just something that you need to accept and know. Copper, for instance, over here, notice that they have a Roman numeral of 2. So this means that when copper does form an ion, it's going to be Cu2+. Often when there's Roman numerals associated with the transition metals, this often means that for that particular element, they could have various ionic charges. You could have a +3, +4, +1. It could differ. So that's why when they give you this particular Roman numeral, this means the net charge must be +2. Iron 3 in this case would therefore be Fe3+. So now we're going to look at these 3 examples over here to determine the ionic compounds with transition metals. So the first one is iron 3 and chloride. We know that iron 3 will become Fe3-, chloride will become Cl-. Follow the crisscross method, so therefore it becomes ACl3. Next example is copper sulfate. So copper, this is copper 2, so therefore this will be Cu2 plus. Sulfate is SO4 2 minus. So the 2 plus 2 minus crisscross with each other, but remember again, if they're the same number, they can be simplified to 1. So our answer in this case is going to be CuSO4. And for the last example, you've got copper 3, so Cu3 plus with NO3 minus in this case, crisscross. So therefore, this is going to become Cu, and we need to include brackets in this case because this indicates there are 3 lots of nitrate ions. So these are just the common misconceptions and mistakes that I often see students make when they're kind of doing these sorts of problems. So the first mistake is obviously, if you got the incorrect ionic charges for the ions, for each individual ions, obviously you're going to get the come up with the incorrect answer. So that's a no-brainer over there. However, number 2 and number 3 is also quite common as well. So what students often do is they actually exchange the subscripts. So what I mean by that is they exchange the lower numbers, the lowercase numbers instead of the subscripts which contain the actual charges. So I'll show you an example of what a student would do if they're making this mistake. So for aluminium nitrate, we know that this is the charge for aluminium. We know this is the charge of this nitrate ion. So when they're making this mistake, what they might do instead is they might crisscross this 3 with aluminium instead of the -1 over here. So in this case over here, what they might have as an answer is Al3, where they've moved this over here, and they've also moved this 3 over here down over here. So that's why aluminium in this case has a 3. We know that this is incorrect. We do not do this. We only exchange the superscripts, or aka the charges and the ionic charges. So your answer for this particular question should be Al bracket NO3 close bracket with a lowercase 3 as well. The third example is not including brackets when there are multiple polyatomic ions. Remember, polyatomic ions are charged ions that contain 1 or more atoms. So nitrate is an example of a polyatomic ion. So I'll show you how that someone would make this particular mistake over here. So when you're not including brackets at all, this is what they might do. They know that they need to crisscross the +3 with a -1. They've done that. But notice in this case, if you put the 3 over here without including brackets, this indicates that there are 33 oxygen atoms, and that's just totally incorrect. Instead, remember, you need to include brackets, so therefore this is the answer that you should arrive with. So please answer these following questions over here so you have a better understanding. So please write down the chemical formula of the following ionic compounds. Pause the video right now so you can answer them, and this is the answer that you should arrive with. One last question for that I would like you guys to do. So this particular review question says the ionic formula of calcium chloride is CaCl2. So that's the correct ionic formula. The question wants you to explain why is the ionic formula of calcium chloride not CaCl. And this again comes back to what I've discussed before, where we said that the net charge of all ionic compounds must be equal to 0. So they're pretty much neutral in this case. So the chemical formula of calcium chloride is not CaCl because the net charge for this particular substance does not equal to 0. And I'll show you why that is the case. So we know that calcium has a net charge of +2 when it becomes an ion. Chlorine will have a net charge of -1. In this case of here, +2 plus a -1 equals equals to +1, because a negative and a positive makes a takeaway. So essentially it becomes 2 take a 1, that becomes +1. So the net charge of this particular substance is +1, not equal to 0. So as shown in this particular diagram above, the net charge for this particular compound is +1. All ionic compounds must have a net charge of 0. And for this particular example, this can be achieved by adding in an extra chlorine atom. When you have an extra chlorine atom, now you've got +2 with a -1 with a -1, therefore the net charge now becomes 0. And that's why the ionic formula of calcium chloride is CaCl2 as opposed to CaCl. This is the end of the video. Thank you guys for watching this. Please leave a thumbs up if you found that this video was helpful. See you in the next video.